Hello, everyone. My name is Nanjan. I'm from Purdue University. Today, I'm going to teach a course, Introduction to Machine Learning. The topic of today's course is perceptron algorithm. The perceptron model was invented at the early stage of machine learning. It was invented by biologists that got inspiration from a real neuron. Here's one example of the neuron. The neurons are connected to each other. For a specific neuron, it will receive input from other neurons, and then the nucleus is going to process those signals and then choose either to fire a signal or not fire a signal as an output. The perceptron algorithm is a model of this process. It has three parts. The first part is the input, which we call it X. It is a column vector X1, X2 to XD. And second part is the parameter of the perceptron algorithm. It has two parts. The first part is the weight. We call it the beta. It is of the same dimension of the input, which is beta 1, beta 2 till beta D. The other part is called the bias. We call it beta naught. This is the real value. Output Y is either positive 1 or negative 1. Here is one graphical formulation. So it has two parts. The first part receives input signal, X1, X2, XD. And then the weight beta is applied on the edge. For this part, it is collecting all the information by doing summation. Beta I, Xi, plus beta naught. And this part, for the second part, is activation. In the formulation of the perceptron algorithm, they choose the sign function as an activation function, and then take this as the output. The activation function, what it's basically doing is, if the function here is evaluated as positive, then it will output positive 1. If it's evaluated as negative, then it will output negative 1. For simplicity of writing, we are going to use the matrix notation. So basically, the symbol we write here is originally beta is a column vector. If we do a transpose, then it becomes a row vector. The matrix product shown on the top is basically beta 1, beta 2 to beta D. And X is a column vector. This operation is basically saying that I equal to 1 to beta I Xi. An important concept in the perceptron algorithm is called the decision boundary. When D equal to 2, the decision boundary corresponds to a line. And the line is defined by this, beta transpose X plus beta naught. It partitions the space into two parts. For one part, they are evaluated to be positive. For the other part, is evaluated to be negative. When D becomes 3-dimensional or more than 3-dimensional, for example, in this 3-dimension, it's no more a line, it's actually a 2D plane. When D is larger than 3, then it becomes D minus 1 hyperplane. So let's look at some geometric property of this hyperplane or this line. So let's assume that a point that is exactly on this line, then basically it will be evaluated to 0 for this equation, X naught plus. This will help us to derive the value of beta naught, which is computed as follows. Because of this hyperplane, for those points that are not on this line, either on one side, either on the other side. So it will have different, if it's on on the upper side, then it will be evaluated to be positive. If on the the lower part, then it will be evaluated as negative. For the second property, we take a look at two different points on this line, which is x1, x2. Because of both of them lie on this line, so we have this equality. Now let's remove those common factors. And we need some further step of simplification. So this is our derived result. Here, beta is a vector, and then x1 minus x2 is another vector. What this equation tells us is these two vectors are perpendicular to each other. So if we look at the figure shown on the right, then it is basically saying that for this vector, then the beta vector is perpendicular to it, and the degree is 90. The degree is 90 degrees. For a point that not on the line, we are curious to know what's the distance of this point to the line. So the distance, the shortest distance is actually can be computed as a projection. So if we pick one point, x naught here, and then we draw a line from x naught to x prime, the distance is a projection. This is a distance. And because we already know that beta is perpendicular to this decision boundary, so we have two vector, beta vector, and then the other vector is x prime minus x naught. The projected distance can be computed as follows. By the linear algebra. If we simplify it, basically we obtain the following result. Now let's take a look at the second part. Because we already know that x naught is lie on the line, so we know that the second part equal to beta naught. So this can help us further simplify it to plus. This is the distance. Well, based on our distance, actually the data point can actually lie on the upper part and lie on the bottom part. So this is not just a distance, but indeed this is a sign distance. It can be positive or negative. So to make this more straightforward, to simplify this, we can take into account the label of the data point. Assume beta and beta naught here can classify this boundary perfectly. So when beta and beta naught, this value is positive, so that the y agree with it is positive. When this part is negative, the y value also agree with it. So we can naturally multiply the two parts together, and this will be our distance by considering either the data point is lie on the upper part or the bottom part. Now, a central goal is to pick a classifier of the perceptron model that can classify the data perfectly. So if we got a data set here, we got several data points x1, x2, x3, x4, x5, x6, x7. So we got two different classifiers. One of the classifiers that can partition the data group of data perfectly. It can separate the two group of data perfectly. However, for the red classifier, you will find that it misclassifies this data point. So we can say that in this setting, if we compare the two classifiers, we can find H1 is better by using the number of misclassified. Actually, we can using this as our cost function, which define that for a fixed value of beta and beta naught, the cost function can be defined as follows. Let's assume that we can get the set of misclassified points, and then for each of them, we are going to compute the distance. Here, let's take a look at this equation. Because this data point is misclassified, this is saying that when the classifier is saying that is a positive label, the ground truth say it is indeed a negative label. When the classifier says that it's a negative label, and the label say that it should be a positive label. So they disagree with each other, and then we put a minus sign there so that we can that everything become positive, and then we can minimize this positive distance. After we define this cost function, a typical way to use the machine learning model is to find those parameter beta and beta naught so that it can achieve much smaller error or much smaller loss in terms of the over the data set. One typical way is using the gradient descent algorithm. It is defined on the parameter of the model, which we call beta here, and also the gamma is the learning rate. If we plot the landscape of the loss, then basically the gradient descent algorithm is starting from a random position. It is going to follow the negative sign of the gradient and then move iteratively till the local minima of this loss, and then the learning rate controls the how fast you're going to move in this loss landscape. And an equation update rule is saying that a new beta can be updated from an old beta by taking into account the step length and also the direction of this update. So in this equation, it requires us to compute the partial L, partial beta. And now let's go back to our loss function and then compute it. So according to our previous calculation, we have the cost function here, and then it is defined as the number of misclassified points, the distance of misclassified points. To compute the gradient, it is actually defined as follows. For the first part, we want to compute the partial derivative with respect to beta. So if we take a look at that, then basically summation will be preserved, and then yi xi will be preserved after the gradient. For the second part, we want to compute the partial gradient with respect to beta naught. It is actually only yi will be preserved. Now we have the loss function and also the gradient. Let's combine the gradient and also the update rule. So one way to do it is beta new equals beta old minus the learning rate times the partial derivative, which is negative I plus 1 yi xi. And also for beta naught, it is similarly learning rate minus I equal to 1m yi. So here we are going to do some simplification. Because we have minus sign here, we can cancel them. And then now we get the whole final equation, which look like that. So what this equation is basically saying that if we look at the data, and then we are going to collect all the misclassified data points and update the beta accordingly. So in the real world, when you have a very large data set, this step will be quite time consuming. Instead of using all the data points, indeed, we can make this operation more cheap by only looking at one data point. So as long as we find one data point is misclassified, we are going to call this update rule. So this is called a stochastic gradient descent, where the stochastic coming from each data point. After seeing this update rule, now we are going to implement as a whole pipeline of the perceptron algorithm. For the first for outlook, it is saying that we are going to do T round of learning up iteration. T stands for the total learning iteration. For the second for loop, we are going to go through the data set. N is the data point size. According to our criterion, we are going to update our parameter when we have an incorrect prediction, meaning when yi is inconsistent with beta xi. So when the model believes that it's positive, so yi is negative. When the model believes it is negative, on the contrary, the yi will be positive. So the criterion is saying that when they disagree with each other, we are going to update our parameter. The parameter we already done is beta equal to a old beta plus learning rate times yi times xi. So beta naught is going to update similarly yi. Another concern is when will this model terminate? When one of the things that we have is called linear separability. If the data set looks pretty well, that they naturally group into two parts, then you will find there are a lot of different classifier can partition this data set into two groups. However, for some nasty data set, that no matter how you draw this line, you still cannot partition this data into two groups. Then we call it non-linear separable. This is linear separable. Then we said for the data that look like for the left part, the model will converge quickly. However, for the data that look like for the right part, the model will always update, and then the performance will always oscillate. So the criterion can be look like this. And if we have some beta, and then also beta naught, they are larger than 0 by a gap delta for all xi, yi. Then we call this kind of data set linear separable, and the model will converge accordingly. After seeing this concept, and now it's a time for us to look at how it actually runs. Here's my implementation, which implemented in Python. It is composed of two parts. The first part is the data, and the second part is a parameter. The rest part is for the update rule. It is exactly the same as we have already just seen. So the first for loop goes through a t iteration, and then the second for loop is goes through each data point. The if condition is saying that as long as we have made a mistake, then we are going to update the parameter beta and beta naught according to our definition. So if we run the algorithm we just seen, and then the feature here is 3D, and then we find that the hyperplane here actually classify everything to the bottom part. So the model needs to update its parameter. It's getting closer. Still, the model has a very great error prediction. So still getting closer. It's still not there. For the fourth step, it's moving. Now it classify every data point to the other part. So the model is still incorrect. If we keep doing so, and we find there's one iteration at iteration 6. So now this time the model can classify the red points as positive, and then the blue points as negative. This is the moment where the model make a correct prediction for all the data points, and the model will converge and terminate. If you are curious to know how the actual how you can run the algorithm, please go through the following link. You will see the actual code. Thank you for taking this lecture.